好的，非常感谢郭教授的分享。那接下来呢，我们再次请出坐标于卫视的 Jürgen 和坐标于香港的郭教授，两位呢将会一起连线，深度探讨抗击疫情、科技的边界与进击。这真是一个令人期待的国际交流。So now let's welcome Jürgen and Yike to have the fireside chat. 请导播将镜头给到 Jürgen 和Yike教授。
Hi, Jürgen. Hello. I think you should turn your microphone on. Oh, great. Got it.
Can you hear me? Okay.
I can hear you now. Yeah, great. Jürgen, very nice to meet you.
The pleasure is all mine.
Very nice. You know, Jürgen is one of the legend of the AI. And LSM, I use LSTM for many times. And one of my paper, which is well cited, is use LSTM to detecting the sleeping stage. We build a sleeping net with EEG, and we build the EEG to detecting at the home base the sleep stage. This was 4 years ago.
That sounds wonderful.
Yes. It's great. We have a great performance on that, and we actually build it into the product. So thanks a lot. It's very nice to see you. And I realized that we're actually dressing with the same style. Right?
It's a great pleasure to be together here. And
we even dressed similar, right? This is I didn't dress the suit, but I didn't realize you dressed a similar thing.
That's how I dress at home. That's how I dress at home.
All right, very good, very good. Yeah. Okay, so maybe we can have a very casual and very open discussion. I realize that our title is about the boundary of the AI, and in this, and also the progress for combating the coronavirus. And I really think this word boundary may not be the quite a right word, because in China, in Chinese, this boundary is have double meaning. So one way you can call it boundary, the other way I think the probably better translation is actually frontier. Right. So the difference between the boundary and the frontier is the boundary is about constraint. You cannot extend it. It's boundary for your country. So extend it, you become invasion. That's not a good thing. But frontier is different. Frontier is the purpose of win the battle, right? You want to extend your frontier all the way to actually move forward. So this extendability is actually quite important. So maybe I suggest we actually talking about this, AI 边界 in the context of the frontier rather than in the semantics boundary. I think that would be quite interesting to talk about that. So maybe I start with a few of my sort of observation first, and then I may actually invite Jürgen to give comments, and then we can have a dialogue. I've really enjoyed your talk, Jürgen, and it is a 20 years journey, but you started with it, right? 1990 you call this the miracle year, right? So, and many things was invented, and many great ideas have the impact now to this AI era. But my view is, I think now we probably, in the, as you said, in your final slides, you said is the dawn of the era. AI means it's a new start, I guess, right? We talk about it. So I was just thinking, what is this new start? Is because now we have so many development, and the deep learning algorithm used everywhere, as you said, and we seem to actually people started to talking about concern about the domination of the AI technology, concern about we will lose the labels and all these things. But in fact, as researchers and scientists in the field, I also share your view completely. We are not really in the sort of in the end. We're probably not even in the beginning of the end. So it's a lot of things just start. So I think in this convex in this virus situation, right? In this compacting virus situation, and we do see a lot of AI applications. Understand the virus and finding out the molecules and find the binding site and understanding the protein structures, and all use our AI technology, as well as we use it to tracking the human contacts, and we design the intervention policy. It's all use the AI, which is absolutely fascinating. And we can see that when we find out nowadays, now we are working on the vaccine, but actually the time to develop a vaccine is actually shortened dramatically, to now from 10 years to now, a couple months probably. So this is largely thanks to the AI technology. This is no wonder about that. So, but I think also we realize AI probably can do much more if we really think about developing AI further in the area to make AI can understand the system more, rather than just predict. In a way, we need an AI to have the is mainly you can think about to build a much better generative model, which can understand the system, can mimic the system, generate all these observations. That would be great. And also how to make the AI, interpretable, and how to make the AI systems, when you do a generative model, I can understand the causality within. I can understand how actually the infection is transformed, what's the infection rate, all these things, and epidemiology. I can actually build a system to model it and to understand within this model what's the impact of the intervention, all these things. So I think that probably also provide a challenge, provide opportunity to developing the next generation of the AI. What do you think, Jürgen?
I agree in many ways, as I always agree with your statements on that. The future is going to be bright. We already have discussed how AI and deep neural networks can contribute to drug design, which I think is almost the most exciting area here, because you really can teach an AI to become a chemist. And then from this chemistry that you have in the model, which your neural network is learning, you can come up with desired chemistry. You can come up with desired products. For example, something like a molecule that can be used in a vaccine for the virus. And in many ways, these neural networks can really learn to produce much faster than alternative methods, candidates that then can be tested in the real world. These AIs are models of physics, they are models of chemistry, they aren't perfect, but they can greatly reduce the options, the alternative substances, the alternative real-world experiments that have to be conducted. And this is really a great opportunity. Whether it's fast enough for the coronavirus, we don't know. Yeah. Whether AI is going to help a lot in the next few weeks and months to beat the coronavirus, that is not obvious, because we need a really fast response, and much depends on just the traditional approach in drug design and the traditional technologies in healthcare. But in the long run, I think we will come out of that with a much better set of options. You mentioned also the limitations of AI, and there we are discussing about something that goes much beyond the current situation, that goes much beyond the coronavirus, that is really going to affect the future of mankind in every single way. You mentioned the explainable AI, and I agree, in mission-critical applications, such as self-driving cars and many applications like that, you have to have systems that can explain themselves, that are transparent, such that if an accident happens, you can really trace back what exactly was it that happened. On the other hand, there are lots of not so mission critical applications where you will have large AI systems that will be creative in a way that in principle is explainable too. However, these systems will be so huge that it will be really very, very time consuming to figure out how exactly did they come up with their new ideas. But that's okay, because as long as they are not used to control atomic power plants or other mission critical situations, you just want to have success. And whether the AI is very explainable or not, as long as it is successful, you will be happy to accept it. In the long run, the only limitation of AI is physics and the limitations of computability, which were identified 80 years ago by Gödel, 1931, when he saw that there are certain things that no computer and no AI system can compute. However, this is not of great practical relevance, and it doesn't affect what we can expect from the near future. In the coming decades, compute is going to get faster and faster and faster at the same rate as in the past. Every 5 years, we are going to gain a factor of 10, which means that in 30 years, we will gain a factor of 1 million. And this means that, well, let me compare that to the currently a large LSTM, like what it has been used to translate from one language to another, has maybe 1 billion connections. However, your brain has 1 million billion connections. So it's still 1 million times more powerful in terms of numbers of connections. However, a factor of 1 million is just 30 years. So in a few decades, and probably long before that actually, you will have for the first time little small devices that will be able to compute as much as a human brain. Not yet, but soon you will have that. And then once you have reached that point, and the trend continues, then it will take only another 5 decades, and you will have for the first time a little small device which can compute as much as all the human brains on this planet taken together, all the 10 billion brains on this planet taken together. And there will not only be one little device like that, but there will be millions and billions and trillions of these devices. And almost all of compute on this planet is going to be not in human brains, but in little machines like that, and they won't really be machines anymore. They will be something that transcends the traditional notion of machine.
Great. Yeah, you're going to understand. But my question to you is, it seemed to me you put a lot of emphasis on the power of the computation in the future. And also because, of course, right, with a powerful machine, you can have a really good platforms to run the advanced STM and neural networks and to get things done. But my question here is here, right? So taking a drug discovery as an example, right? And of course, the powerful computing systems will enhance the speed of screening, and it will find the ligands and find the drugs, what drug candidate, and then much faster than any human beings, and then put into actually the drug design, and then go for it. But I think a human have another power, right? Because a machine can do the chemistry job. But do you think a machine can be a chemist? In the sense, when actually human find a compound, they actually can abstract out, right, its pharmacology, and it can actually predicting its toxicity. So they can actually, from many kind of experiments, come out some principles. Understand that this drug will be applied to this signaling pathway to block, certain kind of the docking sites and terminating certain kind of biological reactions. They can explain it, right? That's not the human's power. That's chemistry. Medicinal chemistry can do this very well. Do you think a machine will ever be able to do that? Apart from like a screen very fast, find your candidates. So that is the sort of the abstraction, right? From observation to build up hierarchical understanding, to form the theory. I think it's just like you, right? You look at the human brains, everybody look at human brain, but you is geniusly come with this idea, right, of the design of recurrent neural networks and put the forget network gate into it and build up abstraction. Do you think a machine can do? I have a curiosity about that.
And my answer is yes, it can
Great.
do that. The current machines are not yet very good at that, but I think we understand the basic principles. Yeah. I think we have understood the basic principles for quite some time. And basically you are asking, is it possible to build an artificial scientist? In science, you need two things. You not only have to take a problem that somebody else gives you, and then you try to find a solution to that.
As an engineer.
Yes, exactly.
Yeah.
You also have to come up with a problem. Yeah. You have to come up with a question. So in science, there are always two important things. Ask a good question, and then find a good answer.
Yeah.
Supervised learning, which is the traditional approach, we just take a problem that somebody else has invented. We just take a question that somebody else has posed, and then the network or the artificial AI learns to solve it by going through a large number of solution candidates and finding one that really solves the problem. However, the important thing is, if you want to be a scientist, you also have to search among the possible questions that you can ask. So you have to search the space of problems until you find a problem that is interesting and solvable in the sense that you can really find a solution to that. There are many problems that don't have a solution that you can find. There are many problems that are so simple, you already know the solution. Both of these problems are uninteresting. But then, in between, there is the sharp line at the borderline of what we know and what we don't know. Right. And now we have to build AIs that already know a certain amount. Maybe they can solve 1,000 different problems. And now the big question is, what should be the 1,001st problem to solve?
Yeah.
And the 1,001st problem should be something that has a solution that the artificial scientist did not know yet. So it's really something new. He isn't able to solve the problem just by generalizing from the previous problems that it has solved. Plus, in addition to that, the problem has to be not too hard such that you can really find a solution. And it turns out there is a way of searching the space of problems such that you always come up with the simplest problem that you cannot solve yet, but which you can easily add to the repertoire of problems, such that your body of strategies for solving problems is growing and growing and growing and growing, always breaking your previous capabilities, always generalizing in a way that requires a modification of the problem solver, such that something comes out that solves a problem that the old problem solver wasn't able to solve yet. And power play is the name of the technique that I just mentioned. So if you look for the power play algorithm, you will find a way of doing exactly that. Not only asking for solutions to given questions, for answers to given questions, but also automatically inventing good questions.
All right.
And our very first way of coming up with an artificial scientist like that dates actually back to 1990. And it's very simple. It's very simple. It's two guys who fight each other. Two neural networks that fight each other. What does the first network do? The first network just takes in the data and produces output actions, and that changes the world. So a baby that is playing with the toys will affect the video that is coming in from its behavior, and it changes what it sees when it's moving the toys around. And that's something that it learns to predict. So there's a second network which just learns to predict the consequences of the actions of the first network. So there are two networks. One does something, and the other one learns to predict the consequences of the actions. Now, everything becomes boring that the little agent, the curious agent, already knows, where it can predict well. It wants to come up with new action sequences that lead to data where the prediction machine is not yet good. So you just give it a reward for coming up with action sequences that lead to data that the other guy, the other network, cannot predict yet. So you have two networks that are fighting each other. Each of them is maximizing the same error function that the other one is minimizing. And in that sense, you have an artificial simple scientist based on two adversarial networks. That goes back to a paper from 1990 that I wrote back then at the Tech University.
Predictability minimization,
And this is actually a crucial aspect of what we are doing in our company, NNAISENSE, which is, to a large extent, really about building artificial scientists that go beyond the simple systems that we had back then.
I know this work where you done the predictability minimization, you call it, right? I remember.
Oh, no, that was artificial curiosity. The predictability minimization is separate. That's also two fighting networks.
Two fighting networks,
what I just mentioned was the artificial curiosity, where you
artificial curiosity, okay. So I followed this part of the fascinating idea, and I think it's great. But now when I look at this kind of paper, I was thinking one thing about the Turing test. So when we're defining intelligence at the moment, right? Turing test is a kind of a golden rule. So we ask a question, and the machine and human give the answer. If the answer is not distinguishable between the human and the machine got intelligence. But your work on the artificial curiosity seems to challenge this Turing test, right?
Yes. So the problem with the Turing test is it is totally subjective, of course.
Yeah.
You know, because usually you phrase it this way: you have a chat between two agents, and the question is, can agent one, who is a human, figure out whether agent two is a computer or a human? And different people are really, some people are much better than others at detecting whether the other guy is a human or not. Everybody who knows a little bit about chatbots is better at predicting whether the other responses from the other guy are really made by a machine or not. And even in the 60s, there was this ELIZA program, maybe the first chatbot, 60s, I think, by Weizenbaum. And back then already, the custodian played around with it, and she was pretty convinced that this is the answer of a human, not of a machine. So it depends so much on what you know, whether this test is passed or not. So it's totally subjective. And a kid will maybe not easily figure out something where an adult won't get fooled.
Oh,
so
sure.
We need some other way of defining intelligence, that is clear. And the way of doing it apparently is look at the set of all possible problems, some of which have solutions, computational solutions, and some of them don't have solutions, and then find the most general agent that is able to solve the broadest class of problems within a reasonable time. And this is what Markus Rütter another guy from Munich, but now a professor in Canberra, has been doing for a long time. And his theory of universal artificial intelligence is really laying the foundations, the theoretical foundations for this approach. He used to be a postdoc and then a senior researcher at my Swiss AI lab, and now he's a professor in Canberra. Universal artificial intelligence, if you look at his book, there you find much more founded ways of measuring intelligence rather than the Turing test.
Yeah, I see. But I guess it's more than just a subjective, right? Because you raise a very important question here, which as a scientist have to do, is ask question, right? Ask question is more fundamental, much more intelligent than answer question, right? So this is not a subjective to answer question or to judge of the answer right or wrong. It's about abstraction, can actually form the facts. You come with the principle and you come with the question to actually to doubt what actually exists. So if Jürgen, you will have a test, what kind of test you can make actually based on your principle of ask questions, artificial curiosity, make observation, thinking something beyond observation, and give human a hard time.
Yes. So how do you measure whether an artificial scientist is really smart? First, let's realize that little babies are scientists, because what they do is they play with the toys, and that's how they learn about physics. And they invent their own experiments. In other words, they invent their own questions. They say, oh, what happens if I take this toy here and if I squeeze it a little bit? Oh, it makes a noise. And then it learns over time to predict the noise that's coming out. At some point, it understands how the toy works. It understands how gravity works and so on. And the toy becomes uninteresting because now it's predictable. Exactly. And then it is motivated to come up with a new question that it doesn't know yet. Now, the baby is interacting with the world in a way that is really different from the way it interacts with the world 20 years later, when it's not a baby anymore, but a grown-up person. And then many of the questions that the baby thought are interesting questions, how do I squeeze this ball such that it makes a noise, are uninteresting to this adult, which it has become over time. So the important point is to realize that in the beginning, although maybe you have still the same principles that you follow as you are trying to explore the world, an adult might think you are stupid, you know nothing about the world. Nevertheless, you have a very intelligent way of exploiting the world. An adult looks at the baby and says, this baby is stupid, it doesn't know anything about the world. But the important thing about intelligence is to learn to become smarter. And the point of intelligence is the improvement of itself, rather than just a general intelligence, which is already given. The nature of intelligence is to fail. The nature of machine learning is to fail, and fail 100 times, but then the 101st time you don't fail because you make a little progress, and that is becoming the basis for the next progress, and so on. And most of life is about dead ends, and most of your ideas about the future, most of your predictions of what's going to happen if you do that and that are going to fail. Nevertheless, sometimes you suddenly figure out something that is predictable and you add that to the repertoire of things that you now understand. And the nature of intelligence is not to solve any problem. No, the nature of intelligence is to learn to solve those problems that you cannot solve yet, and to invent new problems at the borderline between what you already know and what you don't know. And our systems, our artificial systems, are doing exactly that. And so, again, in the beginning, when they are still very dumb, these little systems, they don't look smart, but they look curious because they try things that they haven't tried before. And then over time, they look smarter and smarter because they know more and more about the world they are operating in.
Really? Brilliant.
So the true central aspect of intelligence, this is what we have to measure.
Great. So this has come to my sort of next question. And in your last slides, you talk about your thesis, right? Self-improving AI, and this is your goal, your dream in 1987. Fantastic. That was the time I just came to Britain. So my question here now is, how do you know it's actually improved? Who defined the improvement? Of course, we're talking about in the current machine learning systems or neural network or so on, you know how to judge the improvement because you have loss function there. The improvement is just you do more close that minimize this loss function better, right? You can do. But in what you're talking about now, right, is a much more open and a much more adaptive, right? In a way, it's really truly like a human. But how do you know you are improved? Like what we do in the society, right? I learned something and I feel I'm different from yesterday, but it's very difficult to say I'm improved, right? Because there's some judgment over there, right? So, yeah. But who is going to judge it? So this is really puzzle me.
Yeah. There is no real problem there because, of course, in the real world, there are certain problems that you have to solve. For example, yes. You have to eat 3 times a day, otherwise you will die. So that is a superior goal, which you have to achieve every single day. And it's more important than any of the self-invented goals, which are just about figuring out what happens if I do that and that. How can I predict things that I wasn't able to predict before? And so on. However, you can immediately see whether your curiosity helps you to improve the performance in the really important goals, because as you are learning more and more about the world, as you're learning how gravity works, as you're learning to predict how toys behave if you move them, as you're learning to predict how chemistry works, because you have maybe a neural network that learns about chemistry, you can test the performance of this network in the real world, where it has to solve problems that are given by the real world, such as eating 3 times a day and so on. So what we always have in our systems are 2 little things. I didn't mention that so far, but it's 2 little things. They are, in general, reinforcement learning machines that maximize the reward that is coming in, and there are certain unchangeable rewards. Every day, 3 times a day you have to eat, and that gives you a certain amount of reward. When the battery is low, you are getting hungry, which means that's a negative reward, so you want to avoid that, and you have to invent actions that lead to loading, the charging of the battery, and so on. But on Sunday morning after breakfast, when you already are satisfied, then you may ask yourself, what do I do next? And then suddenly these explorative actions get a chance where you say, maybe today I go to a museum, although although this is not essential for surviving in this world, it still will teach me something because I'm going to learn something by watching these exhibitions in the museum. And whatever you do in this way is going to improve your understanding of what's possible in the world, of what you can do in the world, of how the world works. And this is going to help you to solve better the standard problems of the world. So we have always 2 things. One is the standard reward we want to maximize, and then there is this fleeting reward that you get for understanding something that you didn't know yet, that you get for inventing an experiment that leads to data that has the property that you can learn something from the data about the world that you didn't know yet. And then once this is known, it becomes boring. That's the fleeting reward, the intrinsic reward. And you have to find a new experiment that leads to a new question, basically, that can be answered, where you can find the answer. And that is going to give you this intrinsic reward. But what's dominant is the true external reward for getting enough food per time and stuff like that.
Yeah.
And the measure of intelligence, or the measure of your curiosity reward success, is does it help me to solve the external problems?
Wonderful.
Hi, excuse
Wonderful.
me, professors. Just a
Okay.
kind reminder, there's 5 minutes left. Thank you.
It's too short, too short. Okay, Jürgen, we should find time to actually talk a lot about this. Thank you very much indeed. I learned quite a lot about that. I think what you're talking about is really fascinating, curiosity and problem is a part of intelligence and self-improvement as well. And I think, finally come out with, if I understand correctly, you're also talking about the meta-learning itself have the function to change the utility function, change the rewarding based on the dynamics of the learning, which I learned a lot. Okay, so we only have this time now. Thank you very much. So I hope to see you some point after this all the pandemics. We can meet physically somewhere. Thank you very much.
Yike, it was a pleasure having you interview me, and thank you so much for your presence. I'm looking forward to our next meeting.
Thank you very much. Thank you.
Okay, thank you for your great perspectives. 感谢两位的分享。